Hello everyone, welcome to my channel. So today we are going to do Leetcode daily challenge, binary tree pruning. So basically in this question we are given with the root of binary tree and we are required to return the same tree where every subtree of the given tree not containing a 1 has been removed. So we are required to have all those subtrees in at this particular tree only where there would be a 1. But if in that particular portion of the subtree there is no 1, then we will be directly removing from that. And that is the only algorithm which we are required to devise in this particular question. And a subtree of a node is node plus every node that is descendant to a descendant of that node. So basically the thing is that is we are given with this node, right? So this one and this one, these are the means this is a complete subtree. If only this node is given, then this is a tree as well and subtree as well. If this is the only node, then this is a subtree. Now if we are given with this, this, this and this and this and this and some more nodes are there, then here the thing is that this is a complete subtree, then this is also a subtree, then this whole is also a subtree, then goes here, then this is a subtree, then this is a subtree, and then if we check this is a subtree, no, not this one, but this whole is a subtree. Then if we go ahead and check for this is a subtree because there are no other nodes attached to it, but now this whole would be a subtree because there are a lot of nodes which are being attached to it. And this as a whole, it is also a tree and even a subtree. So like this only, if we are having some nodes attached to it, then it will become a subtree. So this is a pure definition for a subtree. Now comes the part that how we are required to go ahead with our question, because in this question they basically require that 1 is here, 0 is here, 1 is here, right? So if we go ahead and check here, this is a subtree, this is a subtree, this is a subtree, and this whole is a tree as well and subtree as well. Now comes the part, as per the question, we will be removing all those subtrees where we don't figure out with a 1. So in this particular subtree, there is no 1 which is being attached to this subtree, right? So we are required to eliminate this. And then we go to this one. Now already this subtree was eliminated, right? So in its right we are having this one, right? So that's why this subtree would be preserved. And then when we go here, so it itself is a 1, right? So that's why its whole subtree would be reserved. This whole subtree would be reserved. So that's why our answer is something like this. So this is the whole context of this question. Now next part. So the next part is that how we are required to get towards this particular solution. So now in a tree, we can do various sort of traversal in context of DFS, pre-order, post-order, in-order, right? And in context of DFS, we can do level order traversal. So in this particular question, let us just think about the DFS approach of this question and doing a post-order traversal rather than pre-order and in-order. And why I am saying for post-order? Because we are required to remove the subtrees, right? So when we remove from the least node, then it becomes much more easier. You can see that is the approach from these ends. If we approach from these ends, right? So if we approach from these particular ends, I don't know what size. Yeah, now better. If we approach from these ends, right? So it becomes much more easier to remove these nodes, right? Rather than approaching from these ends. So if we approach from the above side and then we strive to remove it and check for the below nodes that are there any subtrees or not, right? So it becomes difficult. But if we go directly towards the end nodes, right, then it becomes much more easier to remove them. So that's why I'm saying that we can go ahead with is root, then left, then right. But whatsoever processing which we are required to do, that we will be doing at the last moment. So basically, we'll go to left, then we'll go to right, and then whatever route is there, we'll do processing on that. So this step would be eliminated. So that is the thing which I'm saying here. So according to that only, now we know that what we are required to do. Now comes the part that how we would be doing the pre-processing part and how we will be proceeding. So the thing is, we will be doing post-audit reversal. That is, first we will be going towards the left subtree, then right subtree, and then we will be doing our main processing algorithm. So how that processing algorithm would be like, means whatsoever route would be there, we'll first check that is it 0 or 1. If it is 0, then that is a sure point that we are required to remove that. And that is not the only criteria, because you can see that here it is 0, but we hadn't removed it. We will only remove it if it is a leaf node, like this. If it is a leaf node, so that simply means that the value is 0, that its left and right child, those are also null, then only we will remove it. And how we will remove it? For removing a particular tree, a subtree or a node, what we do is, we can either directly make it null, right? So that simply means that now we have removed it, and then we can directly return that particular value towards the parent column. That now it is null, so we are required to return it, because in our base condition it's always like that if root equals to null, then we are returning null. And if we make a leaf node as null, then that simply means that now we have removed it, because we are now assigning it as null value. And then in our base case, if we give us that a root equals to null, so we are returning null. So at that particular point only, we will be returning that particular to our parent column. So that's the thing which we are required to do here. So the thing would be that so this was the main intuition behind the same. Now comes the part for time complexity and space complexity. But before that, let me explain you through the dry run. Although I have already explained you that how we are required to build up this intuition from this particular example. Let me check that if there is some more example which can be, yeah, here it is. So here, when we do DFS, now how things go. It will go here, it will go here. So in our stack, first 1 would be there, then 0 would be there, right? Then again 0 would be there. But at that particular moment or point, we have both null, right? So it will be, at this particular point when it gets pop out due to null, because due to null only, it will return to its parent. So when it returned to its parent, at that particular moment, it will be doing those steps which were earlier left. So now it will check, because now it has already checked for the right call. So now it returns to its parent. Now it will check that what is the value. So value here equals to 0, right? And its left and right, both of the child are basically null, right? You can already see. So that's why now we will make this value equals to null. And at that moment only, that particular would be eliminated. So this is the thing. Now this will return to its parent caller, right? So when it returns to its parent caller, now its parent caller will check that do it have some other calls left? Yes, it has. So it will go towards the right call. And here, this particular, because now the stack has become something like this, 1, then 0. So at this particular point, it comes up. So it sees its rightmost, means this one. So it again sees this. But now it will check for left and then right, and when it checks for right, it is also null, so it comes back. So now it is also popped. And as its value is equal to 0 and left and right are null, so again this will also get pop out. And now the stack becomes something like this. So now it comes to this one only. So at this particular point, now it will check that any call left? No. So only condition which is left is this one. So it will check for this. Yeah, it satisfies this, so it will get out, and now the stack is something like this. Just 1 is there, means now it is at this particular point. Now it will check for the remaining calls which is there. So right call was left, so 1 would be pushed into the stack, and then it will check for its call, so 0 would be pushed to the stack. But now the 0 has this also null, this also null, right? So it will return back, and when it returns back, so it will be popped out because of this particular condition, and now the stack, and now it will be eliminated, and the now stack becomes something like this, 1 1, and it remaining call is this 1 1. So now the stack is something like this, and it will pop out, it doesn't satisfy this, it will pop out, it doesn't satisfy this, it will pop out, it doesn't satisfy this. So that's why our ultimate answer would be this one, which is given here. So like this only, we will be returning our answer, means this answer which is there, means 1 null, and then 1, then null, then 1. So our answer would be like this. So this is the thing which we will be doing in this question, and it will come up because of our post-order traversal. So now let us go ahead for the code walkthrough and the time complexity and the space complexity. So the time complexity for the solution is order of n. Order of n is because of the fact when it is a skew tree, although it is now skew tree, but earlier also it could have been a skew tree. So for that context, the time complexity becomes order of n, although it should be log n in the best case scenario, which is equals to height, but in worst case scenario, when it becomes a skew tree, then it would be it would be n. And the space complexity is again dependent on the same thing only. You would have checked that when it is like this, so the space complexity was equal to log n only, right? But when it becomes a skew tree like this, then space complexity as per the height, it again becomes n only. So that's why the space complexity is order of n here. So this was all about this. Now comes the part for our solution, that how we are required to do this particular question. So coding it is pretty much easy, as we got to know that how we are required to do this question. So this is that part which I was saying, the base case part, and then we are calling towards a left tree, then we are calling towards a right tree, right? So after doing all this, then comes the part of our main algo, which we main logic, and that is that if our value is equals to 0 and its left and right both are null, basically it is a leaf node, then in that context we will make that root as null, and then we will be returning our root. So this is the thing which we are required to do in this question. I hope you like the explanation, and if you like it, then please do like and subscribe to my channel, and yeah, please do share among your friends also, so that it could be a greater support to me, because I know I'm really doing pretty much hard work for all this stuff. So yeah, thank you.